Good evening. Welcome to Real Learning Center. We started off on electrostatics for the second PUC, and we have already covered some part one of it. Okay, as I explained in my first class, to learn about electrostatics, you need to know mainly five different words. Okay, most important words. I said that to know those five words, electrostatics is very simple to understand. So, what are those five words? I said electric charge, electric field, electric flux, electric dipole, and electric potential. If we know these words very well, then we understand electrostatics. Okay? So it's all about building the story for these words, and we have done quite a bit of work in the last class for the electric charge. Electric charge we know. So what is the meaning of electric charge? But we are going to now know. We also introduced the electric charge is kind of more or less we understood why there are positive and negative charges. Why do we call them positive, negative, and why, how there are two kinds of things, attraction and repulsion. Hence, positive, negative came about, and we realized that. And we also discussed about Coulomb's law. So, in the Coulomb's law, how electric force between the charges vary as the charges come nearer, go farther. So, we understood Coulomb's law. We also understood electric field. The meaning of electric field we understood. We said when we take a charge, when we keep a charge, let us say I keep one small charge, let us say 2 coulombs plus 2 coulombs, like that we write, okay, plus 2 coulombs. We write a small charge, so around that basically we have electric field, around which there is electric field. But what we said was, if you understand this as some kind of a cloud around the charge, then it is very difficult to solve the question. We need to understand it a little bit differently. So we said that electric field has to be understood as a kind of a force. Electric field is primarily force. If you keep one small charge somewhere here, you need positive charge plus one. That charge, how much force it will experience, and in which direction that will experience. Like in this case, we can very clearly see the force that it experiences because these both are positive, this will be repulsive. Correct? That is the direction of the force. And that force, if we keep a bigger charge, plus 2, plus 3, plus 4, and all that, will be a bigger force because of the Coulomb's law. Now, if you keep only charge of just one unit, that will experience a particular force. And that value of a force, like for example, if you talk about force is always we say K into Q1 into Q2 by R square, where R is the distance between them. Now, what I said was you have to keep one unit. One means Q1 can be anything. Inside in here, we can put 2 coulomb, 3 coulomb, 10 coulomb, 10 to the power minus 6 coulomb, whatever you want, we can. But here, you have to always put 1. Okay. So, if you put 1, then what it means basically is that you will be able to calculate what is the charge, what is the force. Okay. So, now this force that basically we will calculate, that force is nothing but on the unit charge, whatever force is there, that is nothing but electric field. That's what we call it. So in this case, electric field is what? If you keep K and Q1 as it is, and Q2 you will put 1 and then R. So this we call it as electric field. So electric field is KQ by R square. That is the formula for electric field is KQ by R square. So if you are not able to put 1, then you put whatever you want, then later divide it. Like for example, I will put instead of 1, I will put 0.25. Yeah, then I will put it as force basically will be equal to K into Q1 into 0.25 divided by R square. This is the force. Now I will divide this force divided by 0.25. So then basically we call that as electric field is equal to F divided by Q, which is K into Q into 0.25 by R square divided by 0.25, and this will cancel. So this will come also as KQ by R, KQ1, whatever you want to call it, 1 by R. So that means basically either you put 1 unit as the charge or put anything you want, calculate the force and divide it by that. Then you will get the electric. Okay. We also said that electric field is nothing but a vector. If it is a vector, it has to have a direction. So that what is the direction we have to take for this vector? It is the same direction as the electric force. The force is going in this way. So the force is pushing it this way. Electric field has to be in the same direction. So electric field will be in the direction of the force, and its magnitude will be such that this value is 1. Okay. That is all is the definition of the electric. That's over. Suppose if you want to do it here, then the electric field will be nothing but in this direction. And this electric field, for example, is higher than this electric field because this is farther. R value will be bigger here. So since it is in the denominator, the value will become smaller. So as you go farther and farther from the positive charge, electric field becomes lesser and lesser. It reduces the value rate. How much it reduces? It reduces by 1 by R square. And that's how electric field reduces. Now, the question that we are going to ask is, how do I represent the electric field? So, can I write an electric field? Can I draw the picture of electric field? Of course, you can draw. Okay. Let us try to draw the picture of electric field. How does it look like? Okay. So, we are going to take one charge, let us say in the middle, and draw the electric field picture. So, if you take, for example, one charge here, I will take, let us say, 2 coulomb or 3 coulomb, 2.5 coulomb, whatever you want to take. Okay. Take some charge, plus charge. Now, I want to find out electric field at various points and draw it. How do I do it? I will take some point here. Okay. I will put one unit positive charge here, measure the force, and I will, as whatever the force comes, that corresponding vector I will draw. This is the vector. So, this is the electric field at this. Nice, correct? So, electric field at that point I drew, and that is nothing but the force what you get here, nothing but the electric. Now, suppose if I take on any circle, on this circle, anywhere you take, distance from this point to this point is same. That is what is our R, correct? So, KQ by R, in that K is constant, Q is constant, R is constant, R is not changed if I take it on this. Let's say I am going to take it here. So, R is same. So, the value of the electric field will be same. So, value of the electric field will be same. That means the length of the vector is same. So, I am going to basically write here, this is the length of this is the E. This length and this length are same, correct? Because they are from equal distance from the center. Wherever you want to draw, you want to draw it here, so it will be like this point will be same length, but its direction is so everywhere you can draw. It is just basically nothing like a arrows, like from sun all the arrows are coming up, no? Out like that. So you can actually put all these arrows, very nice arrows, looks also beautiful like this. These are basically the electricity. Please observe one important thing, that is these arrows are all of equal size. That means their magnitudes are same, but their directions are different. Okay. So that means this is we are representing electric fields at various points. Representing electric field at various points. Now suppose I want to represent electric field at some other point. Okay. At this point electric field if I represent, this also will be repulsion. But see that these direction of this and direction of this will be same. Both are repelled in the same direction. But this electric field is smaller. Can you see that? Why? Because the distance is larger. The distance is farther. Electric field reduces by 1 by R. So it becomes smaller. So every point on this circle will have smaller one. Correct? Will have smaller one. Right? So as you go further and further, the electric field values, the magnitude of the electric field will reduce. If you go even further, here it may be a very small atom. Correct? Right. So as you go further and further, the arrow length will be decreased. So this is how we can plot the electric vector around a charge. Okay, this is how we can plot actually. Okay. However, what really happens is this kind of a presentation of electric field and drawing them like this has one simple problem. One problem we have. What is that problem? So let us understand that problem. One single problem. So suppose I want to draw what is the electric field here. Correct? So I should be able to draw electric field at every point. I will let us say want to draw it here. Now it is a practical problem. I'm going to draw an electric field here. It will be shorter than this but longer than this. It will be somewhat like this. Correct? Now what happened is this arrow mingles with this arrow and you don't know where is this arrow starting. So it's difficult to draw this arrow. So even if you want to do it somewhere here, again you will overlap. So all these arrows, if you draw electric field to nearby points, these arrows will overlap and we can't actually measure the length of the arrow and tell how much is the magnitude. Generally that's how you measure. Given a vector t, you will measure the length of the vector and say this is the magnitude. So it's not possible to do that. So this way of representing the field line, electric field vector, is nice but has limitations. Limitations, you understood what the limitations are. It is basically having the difficulty that these arrows, if you want to take at different points, they will overlap. So what do we do? So let us invent a new way of representing. So that new way of representing is what is called as electric field line. Electric field line is a way of representing electric field, which is not the normal vector representation. It's a very different representation, but very interesting. How they solved this problem is pretty interesting. I hope you understood why this problem is there. When you take electric field at nearby points, these arrows overlap. So I want to avoid that overlap. So what do? I create a new way of representing electric field. So let us see what is the way of representing. Okay. So I'm going to erase this round part here. My electric charge will remain there. Okay. Now, new way of representing electric field is anywhere you take electric field we will only show first of all the direction of the electric. We'll worry about the magnitude later. At all these points here, electric field is in this direction. Correct? I'll put it there. Some arrows, just one direction. All of them are pointing there. All the points here are pointing there. All the points here are pointing. Correct? So you can put one or many arrows, doesn't matter. So we are not showing any particular magnitude. We are just showing the direction. Correct? We are showing the direction of the electric. Like this, we will show direction of it everywhere. Okay. So these are called electric field lines, or we also say field lines, lines of force, because we put a unit positive charge, they move in that direction. They are called lines of force or electric field lines. And these electric field lines, see carefully, they are representing all the magnitude, but they are not showing any. They are not showing any kind of a direction. They are showing only direction. They are not showing any kind of a magnitude. Okay. So you look at the magnitude of how does it work? Okay. Is it possible to find out the magnitude using this? It's not, because we can't measure the using a scale. Correct? How do we measure? It's not possible. So we still have to find the magnitude. So what we do is basically we will say that the density, the density of the line represent the magnitude. It's a pretty complicated thing to understand. It looks like, but it's not that complicated. What is the meaning of density of line? See, now please understand that these arrows are, don't assume that these arrows are on the on the only on the board. This electric field, if you keep, arrows are coming this way also. Correct? It's a sphere. It's like arrows coming in all directions. So it's like a complete spherical outflow of arrows. Okay. So in such a scenario now, if you take, for example, any one small place, one small surface on that. So let us say I'm going to take it here, small surface, okay, some area, surface area, and that surface would actually have multiple arrows in that. Correct? So the number of arrows I will count for a given surface area. So the surface area here is this much. So there are only two arrows. Now I will take the same surface area nearby. Same surface. Now you can see that 1, 2, 3, 4, 5 arrows, 4 arrows are there. So if there are more arrows passing through a given surface area, the surface area you have to take equal here and here. Okay. So if two surface areas are equal, if this has got lesser number of arrows passing through that, if this has got more arrows passing through that, that means in this place the magnitude of the electric field is higher. Magnitude means more power, and it is proportional, more power. Now, however, please understand one thing. You may say it depends on how many lines you basically have drawn, but you can draw millions of lines. So we are not very much worried about exactly how many. We are worried about the ratio. In the sense, the number of lines. Once you draw, you draw. How many lines you want to draw, you draw. After drawing all the lines, then you take one area. In that area, how many are passing here? How many are passing here? How many are passing here? If you keep taking that area nearby, you know that more and more lines are passing. That means the magnitude inside near to the charge is very high. So what we are saying basically is electric field is higher near the charge and lower away from the charge. So it is somehow giving you an idea that electric field representation, what we are giving as a field line, is not only giving the direction, but it is also giving the magnitude. But the magnitude is given in a very indirect way, not as direct as before. Earlier we just measured the line, length of it, and that gave the magnitude. Now what you are doing is you are measuring the number of lines that are passing, kind of a density. That's what we are doing. Hence, this electric field lines method is used to draw electric field because this is doable. You are not having a overwriting problem. So, simply arrows are written, so no question of overwriting. They are giving only direction. So only magnitude is given by some other way, which is density, number of lines. Hence, what we say here is electric field lines have to be represented as this kind of a field lines of force, we call it. Okay. So if you understand this, that means we know how to draw field. So you may be basically asked to say how field lines represent both magnitude and direction. So you can say direction of the field lines are given by the arrow. Magnitude of the field lines are given by the density of the arrow. These two statements are sufficient to explain field lines. Okay. So let's move forward. I hope you understood what are field lines, why are they required. Now we are going to basically utilize it more in defining what is electric flux. Electric flux is a very interesting. We'll talk about electric flux. Okay. So electric flux is one more parameter, okay, one more word that we need to understand in our uh, electrostatics. So flux is a word that is used not just in electric uh, fields and electric charges and all. It is used in many places. Even water flux is there, current flux. So we use this word in many places. The flux is simply nothing but how much of it is going in some certain direction. How much? That is basically flux in a given cross section area. Now you see here, for example, electric flux that is passing through any given area is calculated by the number of lines that are going in that area. Okay. How many lines are going in that area? That is basically so. But however, you may ask, isn't it basically dependent on number of lines that you are drawing? Yeah, but how do we draw to make electric flux basically exactly calculable? Yes. So we say that electric field lines are there and they are passing through that area. Now electric flux is given, but flux is given by a symbol called phi. Okay. We call it's just a Greek letter. Okay. Symbol called phi. Phi. Okay. Now this is nothing but the total area that you are passing, whatever the area A, into electric. So just multiply the area into the electric field. So electric field, whatever is there, that amount electric field is the value that you can calculate by using KQ by R. Okay. Now that value into the area, if you calculate, that is nothing but so electric flux is nothing but total amount of electric field that is going through certain area. So it is like saying how many, what is the cost of 10 bananas? So we'll say 10 into cost of one banana, right? So this is like cost of 10 bananas. This is like one banana. So 10 into 1, 10 into the cost is total cost. So a simple basic ratio. Okay, what we are saying basically is electric flux is nothing but electric field into the area that flux is passing. However, there is one caution that we need to take care in defining the flux. Okay. This is where your uh, second PUC understanding of vectors will come into picture. If you had understood vectors in the first PUC, then it is easy. Otherwise, it is a little bit complicated. So we want to say that electric field passing through the area in the perpendicular direction. Okay, in the sense that we don't use, if you look at this, we're going to make it slightly interesting in mathematical way. Okay. We say flux is a scalar quantity. It doesn't have direction. And we say E is a vector. Okay. And area is just a number. Okay. But we will consider area as a vector. Area is just a number, but we consider area as a vector because if area is like this, okay, we say that this is the area vector. So whichever is the some perpendicular line that we draw and say that is the area vector. The length of this vector is equal to the area, and this is perpendicular to the area. Suppose if you draw like this area, so this is the area vector. If you draw some other direction, this is the area. So area vector is always telling us how the area is aligned. Area is like this, like this, like this. If it is like this, vector is like this. If it is like this, vector is like this. So area vector is perpendicular to the area. So it somehow gives the idea of the direction of the area. Okay, so that's the meaning of a vector. Now when you have two vectors, area is also a vector and E is also a vector. Two vector when you multiply, you have to get scalar. means you have to multiply using a dot product. A dot product is given by E magnitude into A magnitude into cos theta. That is the angle between the vectors. So that means the area vector and the E vector is magnitude. It's basically angle between those two vectors. You have to count, calculate the flux. This is only the slightly tricky part. So I will slightly explain it in a diagrammatic way for you to understand. Okay. Let us say this is my flux. Flux is not arrow outside, but now in our case it's parallel flux. So if that is the flux, and let's say if I have an area like perpendicular to passing, okay. So the same flux, let us say I will take like continue. Okay. But this time I will have another area which is actually having certain angle. Okay. So this is my area A1, my area A. But remember that when you get an angle, that means this area is bigger than the A1. Okay. It is bigger than A1. That means A1, A2. Why is it bigger? Because it is angled. Okay. And to be able to, say it's like writing like this. If I have one line here and one line here, okay, this line has to be bigger than this line. So hence the area will be bigger. Correct. So this area is bigger. A1 is smaller than A. Correct. So however, we realize that basically the flux that is passing through this is same in both cases. If I take the value of E and multiply with this, I will get a bigger number. But that is not the flux. Flux is what it is passing through. So what do I do? So I actually take the cos. Cos theta gives us an idea that why is cos theta? Look at this. The vector, basically what I call area vector for the first one is perpendicular to the area. So this area is like this, means this area vector is like this is the area vector for A1. For A2, the area vector is because it is perpendicular to this area. Okay. Now between these two areas, look at this, the angle. So this is the direction of the E and this is the theta. In this case, E and theta are both equal in the same direction. Now you see cos theta, okay, A2 cos theta. So what will happen? A2 cos theta. A2 cos theta will be a smaller number. So if we multiply A2 cos theta to the E, then that will be equal to A into A1. So A1 actually equal to A2 cos theta. Hence, the flux between these are exactly same. So it's like saying that if I take a pipe, okay, if I take a pipe and cut the pipe, water is flowing in this pipe. I will cut the pipe like this. So some water comes out. Per second, I will get, let us say, 10 liters of water or 5 liters of water. Now, instead of cutting like this, if I cut the pipeline, though the area is bigger, okay, will I get more water? Think about it. Because water comes here, the same water coming out, I will still get the same amount of water. That is called water flux. So just because you have cut the pipe in a different way, how water flux does not change. Same way, if we keep area in a different angle, amount of electric flux in that area is not going to change. And hence we use the dot product. That is the reason we use a dot product. to make sure that this happens, because our real world tells us that that is not going to change. So now our math will basically have to be the same result. Hence we use the dot product. So we always think the other way around. It's not the math first, it's the real world first. So math comes later. Okay. So hence, please understand that E dot A is what we have come out with as a mathematical representation. What happens in the real world. So in the real world, this basically water is same whether you cut it this way or cut it. So to make it the same way, we use the dot product so that we can multiply cos theta and we keep it same value whichever way you cut it. Okay. So I hope you understand what is the meaning of electric. Electric plus fundamentally is just electric field into area. But the area, if it is cut in the wrong direction, how to take it as the correct area. For that we need a dot product. Otherwise we would have simply multiplied. Okay. Dot product is just because. So I hope you understood what is the meaning of electric flux. Okay. So that is the fundamental meaning of electric. Now we're going to move forward into a very, very interesting area. That's called Gauss law. Gauss law. Gauss's law or Gauss law. So when the Gauss law is stated in a mathematical way, looks ununderstandable. But if it is stated in a common sense way, you will be able to simply understand. Now I will try both of them. You can see why I say this. Okay. So Gauss law I am going to state in a mathematical way first, and you will see you won't understand. Okay. Flux around flux through a closed surface is equal to, let us say, phi is given by integral of, see what we are doing, integral of surface integral. It's called surface integral. It's a circle here. For a closed surface, we call it a circle. Surface integral of A dot ds is equal to 2 by. This is basically called as Gauss. You can write it basically in the form of sigma. We can say sigma of E dot delta S equal to 2 by. You can write like this. Anyway, important point to understand is this is the meaning. This meaning of this is what? How can this be simplified? What is the meaning of E dot ds is equal to q by epsilon? So I will give you some simple examples. Then this law will become very clear. So let us say I have some kind of a, let's say, a ball. I have a ball, a small ball, okay, tennis ball, any ball. Now I will keep this ball in the middle of, let us say, some room, or a circular room, or a cylindrical room. It doesn't matter. Some room. I'm going to keep it. I'll keep it as a cylinder. For simplicity, I'll keep it in a circle, in a spherical room. There is a spherical room. I'll keep it in a spherical room. And what I will do is I will basically take a small bomb inside, like a Diwali bomb, and blast it. when I blast it, what happens? This ball will become small pieces. This ball will become what? Small pieces. And those pieces will fly away. All become pieces and they will all fly away. One piece will go like this, go like this. So lots of pieces. So many pieces. They will all fly. Correct? Small pieces. And let's say those are going to penetrate the covering, spherical covering, make holes inside that, then go away outside and I will collect. I'll collect all the pieces. Okay. So what I will now do is I will just check how many pieces I have collected and what are the sizes of these collected. So if I join all those pieces, I will get the ball. What I'm doing, I'm adding all the pieces. Joining is adding all the pieces. I will get the ball. And it does not matter how big is this sphere or how small is this sphere, whether it is a sphere or not, as long as it is a closed surface and as long as all the pieces fly away, no pieces just fall inside, they'll all fly away. That happens. Then by collecting all the pieces on the surface, I'm collecting, where am I collecting the pieces? I'm collecting the pieces on the surface and joining them, putting them together, adding them, I will get the ball. Okay. This is Gauss law. Why is this Gauss law? How is that law related to this equation? Okay. What we are doing is basically in this equation, E dot df means we are basically taking area into E is what we call as a flux, correct? So flux is nothing but what is the electric field that is passing through every piece, basically what is the electric field that is passing through. Like if I take a charge here, if I keep a charge here, plus Q, and put a sphere around it. Now electric field is going in all field lines if I draw. The electric field is going in all directions, correct? Just like my blast, electric field is going all directions. So if I take an electric field here on the surface and multiply the electric field with the area, I will get total electric field that is passing, the total flux that is passing through the surface. Total flux means what? All the pieces added together. All the pieces added together. Each piece is one small piece. All that added together is the total flux. Here also, all the small values of the area into E that I added together with the total flux. And that total flux is nothing but the inside ball, correct? So here also the total flux is nothing but the inside. That is it. You may ask, what is this epsilon naught? Epsilon naught is just basically handle the units because our charge units and flux units are different. To convert the unit, we keep epsilon. Otherwise, it is basically nothing but simply the charge. Yeah. Correct the units, we are not, don't worry about that. You need to use it, but it's not playing any other role. What we are saying is that simple statement that we are saying, when some blast happens, flux that is going on the surface, if you add all of them, that will tell you how much has been blasted. What is the source? So if a source is not just blasting, let us say it's a fountain, it is giving water to a very person. If you collect all the water around it, you will know how much water has been sent out. So if you go to the surface and collect everything and add them, that will give you what is the source. And that statement is nothing but the Gauss law. That is called Gauss law. mathematical expression of such a gas. Integration is nothing but summation. Integration over S means on the whole surface we are adding everything. That is the meaning of integration. Okay, so all that I am adding, and that when you add together will give you the source. Source is nothing but the charge. Epsilon naught is only for the sake of changing the unit property. So this is the meaning of the gas law, and I hope you got some understanding of what is the meaning of the gas law. So this if you know this meaning of the gas law, then understanding a lot of applications of the gas law and how to use gas law to calculate something is very okay. So let's try. So this is the basic gas law. I'm not going to do the proof and all. That and all you will look at the textbook or notes like some other people. I'm only giving you the conceptual understanding. So let's look at the applications of the gas law. What are the different applications of the gas law? How do I use this gas law? This is a very interesting law. It's a very simple insight. No complications here. Correct? So we'll try to see whether how to use this gas. And let's try. Okay. So when you want to use the gas law, where do you use? Generally, gas law is used to calculate the electric field in a simple way. If you want to calculate electric field, it's generally very easy. Okay, it's not very complicated. Let's say if I have two charges and I want to calculate this charge is plus 2 coulomb, this charge is plus 3 coulomb. I want to calculate the electric field at this point. It's not very complicated. What I will do is I will find out that this electric field is like this, and I will calculate that this electric field is slightly bigger because it is big. Okay. Now, the resultant electric field, this is the electric field due to 2. I'll call it as E due to 2 coulomb. This is electric field due to 3 coulomb. So, the resultant electric field is the vector sum of these two. This thing. And how to calculate vector sum? So, you can calculate vector sum by formula. So, there is a formula for it. So, we can say that E is nothing but E is equal to okay, E3C square plus E2C square plus 2 E3C into E2C into cos theta. This is E square, where theta is this angle. So this is the formula to add calculate. This is not a Pythagoras theorem. If it is 90 degree, you can simply use Pythagoras. If it is not 90 degree, then you have to use this formula. This is the formula you can use and calculate. So now when you have two charges, it is easier to do. When you have three charges, it's still easier to do. You can calculate this in two charges, and again, let's say third charge is here. So then you can calculate its electric field and add these two to get the final electric. So like that, you can keep doing for any number of charges. But the number of charges is too much. Like it is a continuous charge, continuously charged, a line of charge. So what do you do? How do I add? That's a complicated thing. For example, we are going to take one simple scenario and show you how complicated it is. Let's say I have a line. And in physics, we have this habit. Whenever we draw a line, we don't say that finite length. We say infinite length. That means the line is basically there in both directions up to infinity. And this line is charged, uniformly charged. An infinite length of line is uniformly charged. So what does mean? That means it has charges deposited on it everywhere. Uniform. So plus, 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 plus. Small values of charges continuously deposited. Continuously means there is no space in between. It means very neighboring to each other. So nice. That's why I have charges. And I will ask a question. Because of this is infinite line. What is the electric field at this point? At a distance, let's say 10 centimeters, or let's say r. r. So at a distance r, what is that? How are we going to calculate? That is the question. So now, if we use our normal method to calculate that, I have to take piece and pieces of each electric field, and I will calculate how much the electric field for this, because of this, how much is the electric field, because of this, how much is the electric field. All those electric field is finite number of ones I have to add, and it's very complicated. Adding finite. So, or we will be, if you are intelligent enough, if you know how to do the integration, you can create an integration for that and add it using integration. That's also doable. Not that it is not doable, it's just complicated. So Gauss's law, okay, help of Gauss's law becomes very easy to add. How? Let us see. Okay. So what I will do is I will take one single cylinder. I will take a cylinder. Okay. Like anyway, I mean, cylinder can be taken at this point or around that point. Somewhere. Let's have it easier. So what will happen if you consider a cylinder? So you will be able to find out if you take this cylinder. The cylinder is nothing but this. What is the cylinder? The cylinder is a closed surface. Closed surface means both sides are closed. Remember that I am taking a imaginary cylinder, not a real cylinder. Okay? This whole surface is closed here and top also closed, everywhere closed. It's closed surface. And if I take electric field on the top everywhere, then if I add all the flux, that must be equal to the charge. Okay, let's say this length of this is some small l. Okay, and this has a charge density. Let us say lambda. Lambda means some number x, whatever. Lambda basically lambda coulombs per unit length. Coulombs per meter. That is the linear charge density. Now, if you want to calculate the electric field here, so I will say that let there be an electric field E on. Okay? Let there be an electric field. And this electric field, I am going to prove that it will be in this direction. It's not going to be in any other direction. Why so? Because if it is in any other direction, let's say the electric field here is gotten by adding the electric field that is coming from this side and electric field that is coming from this side. From both of the charges, this charge here and this charge here constitute electric field. Correct? So the charge here, for example, constitutes an electric field here like this. Charge here constitutes an electric field like this. Correct? Now this electric field, if I take two components here, one component horizontal, another vertical. This also horizontal and vertical. Vertical components are opposing each other and they cancel out because I have taken the same distance here from both sides. This distance basically is same as this distance. So they cancel out. Only horizontal components add. So our what we are knowing behavior here is basically from here to here what is the total length and here to here total length are equal. Okay, because both are infinite, right? We are having infinite length this side and infinite length this side. They are cancelling out. So because of that, no vertical component will remain. Only horizontal component will get added. So we know for sure that electric field is only in the horizontal direction. It's not in the vertical. It's all cancelled. Correct? Everywhere on this. This is applicable for any point because infinity is there on the top and the bottom. It's a very small distance. Now, anywhere you go upside and downside, both sides. So everywhere electric field is E in the horizontal direction, and the distance from here to here we are taking it same because it's a cylinder. So everywhere it is E, and it is basically horizontal, horizontal, radially outward. If you draw a cylinder like this here, it is like horizontal and radially outward. Everywhere horizontal and radially outward. So it is like an arrow on all sides of the cylinder. That is the electric. Okay. Now that is electric field is same everywhere, all these areas. So total flux passing through this is electric field that is coming out of this, electric field is that is coming out of the bottom, electric field that is coming out of the side. Correct? Total flux is equal to flux top plus flux bottom plus flux curved surface. All of these fluxes, if you add, you will get the total length. So, you see here, flux top is how much, flux bottom is how much. Okay. Flux top actually, look at the area. Okay. Area vector is in this direction because this is the area. Area is perpendicular, area vector is perpendicular to the area. So, electric field is going in this direction. The angle between them is 90. Hence, phi is equal to E dot A. When you do, you get 0. I mean, it's simple because there is no flux actually crossing this. Because flux, all the electric fields are horizontal. Nothing crossing this. Nothing crossing this. So, phi at the top and phi at the bottom are both 0. Only phi at the curved is what is there. Okay. Which is E everywhere into the area. The area, surface area of that one is 2 pi r into L. Correct? 2 pi r is the circle into L, that is the length. Total surface area is 2 pi r into L. Okay, that is the total flux. Okay, into basically that is the area into E. 2 pi r into L into E is the total flux. So the total flux is simply equal to 2 pi r into L into E, which is what it is phi. I don't have to do any integration. I just have to write what is the total flux. 2 pi r into L into E. Total flux. So Gauss law tells us that this total flux is equal to Q by epsilon naught enclosed. Inside whatever is enclosed, it's Q by epsilon naught is the value equal to total. So Q is how much? Q means total charge enclosed. You see here, the charge enclosed is nothing but this wire from internal wire from here to here. So here to here length is L, and it is lambda coulombs per meter. So it is the charge density, linear charge density into length is the total charge. So linear charge density into L is the total Q. Q is nothing but lambda into L. Okay. And divided by epsilon. So we are able to now write the Gauss's law for this scenario. We have now, please understand what we have done. We have taken actually, our goal was to find out electric field. Okay. So we tried to apply Gauss law by taking a imaginary cylinder and that cylinder, and we made our arguments to show that electric field is only in the horizontal direction. So no flux passing through top and bottom. So total flux only is in the side. That is given by 2 pi r L into E, because flux is equal to area into electric field. That should be equal. Flux should be equal to Q by epsilon. Q is the enclosed charge, enclosed charge means what is the charge inside the cylinder? Charge is only here, from here to here. So lambda is per unit length. So total length is L, so it is lambda. Now once we write this, we suddenly realize that we can calculate E based on this. E everywhere is same. Therefore, L gets cancelled. It is E lambda by 2 pi r into epsilon. So we found out the total electric field at this point P. At not only this point P, at all points on the cylinder, electric field is given by lambda by 2 pi epsilon naught, and the direction is radially out. Okay. This is how we can use Gauss's law to calculate electric field. We can use the same Gauss law to calculate electric field in few other scenarios, okay, which time permits I'll explain in the next class. But I will actually also do electric dipole and electric potential as my next steps. Okay. Next class will be electric dipole and then electric potential. If I do that, most of the electrostatic concepts will be understood. And under the electric potential, if you go to second chapter, actually there is capacitance to cover capacitance.